Now we are coming to our next presenter, which is Richard Krumpolec. Okay, and he is giving us a presentation about fast and effective large area cleaning and activation of float glass with improved micro-uniformity by atmospheric plasma surface processing. He is a researcher at the R&D Center C-Plant at Masaryk University in Brno, Czech Republic, and I think the stage is yours.
Thank you. Good afternoon. I came from the university, from the R&D center in Brno, where we are doing the plasma physics. Basically, what we do is we study electrical discharges, the sources of plasma, and then we try to utilize them for various applications. What we do is that we take this plasma and we try to modify various materials. It could be polymers, metals, but of course, one of the material we are working on is the glass. And here in this talk, I would like to show you how we can utilize plasma modified glass for enhancement of laminated glass, which is used by plasma-treated glass surface. Therefore, I will introduce you to our atmospheric plasma technology, which is called DCSBD. And then I will show you how this plasma treatment will affect the surface of glass. After that, I will show you how this plasma-treated glass, when it's used for the laminated glass, can improve the properties of the real product. So, we know that the laminated glass is composed of glass panes and then also the interlayer. And it's clear that for the properties of the product, it's important to ensure very good surface properties of the glass surface and also maybe the interlayers. And very important processing step is the cleaning process of the glass, because of then it will somehow it can modify the final properties of the product. And we know that there are some standard ways how we can clean the glass, but there is a way that plasma can probably make it even better. So for glass, we know that it's important to have a clean glass, to have a good uniformity, and also maybe to create some functional groups on the surface. And why we need this? Because of it's important for the mechanical and visual performance of the laminated glass. For example, the uniformity is especially important when we would like to prevent any formation of defects or delamination on the edges of laminated glass. And of course, the functional groups are very important if we need very good bonding between the glass and the interlayer. The conventional cleaning is very clear. Basically, it's done in some washing machine devices. There is a typo. It's done by, for example, conditioned water. But this process is not very fast because you need to clean these glass sheets, panes, and then you need to dry them. And I would like to present you an alternative for this process, which could be plasma treatment of glass. But of course, we would like to apply plasma in the real process. The process needs to run at atmospheric pressure. It needs to be very fast. It could be effective in the way of the cost and also how it's applied. And also, we would like to finalize the research or development of this technology. It should be compatible with standard lamination lines on the real machinery. So first of all, I will present you our plasma technology. But first in this slide, I would like to tell you what is plasma. I don't know if you have experienced this, but basically plasma is electrical discharge. It can be generated at atmospheric pressure or low pressure, but we of course prefer atmospheric pressure because then we don't need any vacuum systems, for example. And plasma, what is important, is source of active species which can then affect the surface of modified material. It's composed of energetic electrons, ions, metastables, and other species. And the effect of plasma on the material is that, for example, there are different various effects. We can change the wettability, we can change, for example, hydrophobic surface to hydrophilic. We can clean the surface, so, for example, we can remove some surface contaminants. And we can also do some modification or some activation in the way that we create some functional groups, which can then increase or improve the adhesion, for example, to interlayers, especially in laminated glass. In our work, we are working with atmospheric pressure plasma source, which is called diffuse coplanar surface barrier discharge. Very long name, but I will use only the abbreviation DCSBD. Basically, this plasma system generates very thin plasma layer, as we can see here in this image. On the surface of this white plate, we can generate very thin layer of plasma. The dimensions are roughly 8 to 20 centimeters. And the thickness of this plasma is only 0.3 millimeters. It's effective thickness of the plasma, which can be used for treatment of the material. The thickness is not very large, but on the other hand, we can achieve very high power density and also very effective treatment of the material, and especially for flat surfaces like float glass. In our case, we will work only, or we are working in this work only with ambient plasma. So the plasma is generated in these ambient conditions. The discharge looks like this. It's a very robust system. You can even touch the plasma, this electrical discharge. And if you change your fingers, your hand with some material, you can activate it, you can change its surface properties. There is no problem to plasma treat really large materials. For example, we can take many DCSBD plasma units. We can create plasma array like this. We can treat really very large materials. This plasma can be used for modification of various materials, and also one of them are glass and, for example, polymers, which is interesting also for treatment of interlayers. So, what happens when we treat glass by DCSBD plasma? In this model experiment, I will show you the results. We work with the soda lime flow glass. Basically, there is no limit for the thickness of the glass. We can work with thin glass, but also with very thick glass. This plasma can be generated in a wide range of temperatures and also relative humidity values. And since the power density of our plasma system is very high, we can achieve very short treatment times. It means that the exposure of our plasma, of our glass surface to the plasma is very short. Typically, it's only a couple of seconds. So the process is very, very fast. And then I will show you how we treat the sample, and after that I will show you some results. This is the visualization, how we treat the material. We take the piece of glass, we expose it to the plasma, and then we can use it. The ways how we can treat the glass are various. In the first case, or one option is that we just take the sample, it's the laboratory case, and we through the plasma area. Or we can take, for example, stable piece of glass or sheet of glass, and we can move with the plasma source over the surface we would like to modify. Or in the option C, we can take, for example, a stable plasma unit. It can modify very long, basically unlimited length of the glass. For example, in the factory, where you have a very long piece of glass sheet. So let's go into the results. If we apply the plasma on the surface of glass, we can see very rapid decrease of water contact angle. Water contact angle is a value which can assess the wettability of the surface. We can see that even after 1 second, very fast treatment, there is a very sharp decrease of this water contact angle. We can also measure the adhesion of the plasma treated glass, and as you can see here, these two graphs, one of them is for as received glass, and one of them is pre-cleaned glass. We can see an increase of adhesion properties. This was measured by standard adhesion peel tip using this ICO test. What is important is that plasma can clean the surface. It means that we can remove some organic or unorganic particles or any contaminants on the surface. And we used for analysis X-ray photoelectron spectroscopy. This is the method which can be utilized to measure very precisely the concentration of elements on the surface of plasma-treated glass. And here, for example, here we can see that when the as-received glass carbon concentration is around 57 atomic percent, and if we compare it with the cleaned, standard wet cleaned glass, the concentration is around 21%. But on the other hand, when we apply plasma for very short treatment time, the carbon concentration decreased to only 5%. We can calculate, for example, the oxygen to silicon ratio, which represents the cleanness of the glass. We can see a rapid decrease from about 3.6 to about 2.3, 2.4, which is very close to 2, which should be for clean glass. The carbon to oxygen ratio represents the contamination, and we can see that there is a sharp decrease from more than 2 to less than 0.07. Regarding the activation, because we are not only clean the glass, but we also create some surface functional groups on the surface. We analyze it again by XPS method. We revealed the presence of these oxygen functional groups on the surface of glass. And we calculated again the oxygen to carbon ratio based on the ratio of hydroxyl carbonyl groups related to pure carbon bonds, and we see that plasma treated glass and the content of oxygen bonds on the surface is more than 60%, and this change we observe this change only after 4-second treatment. In comparison, reference sample is on the half of this, roughly on the of this value. In our work, we analyze also the micro-uniformity of the glass because of this micro-uniformity is especially important for this delamination effect, for example. And therefore, we created some map concentrations of the elements, especially carbon, oxygen, and silicon. And you can see here in this top left graph that there is a huge variation of the carbon element on the surface of glass, on the surface of as received sample. There is a change from this red color up to the green one. And also when you compare it to the wet solvent clean glass surface, there is some improvement in the uniformity, but it's not best one. later in the next slide, I will compare it with the plasma-treated glass surface. What is important, I haven't tell you that the dimension of the sample which was analyzed is more than 1 squared centimeter. And here in this slide, we have a comparison of as-received glass, standard wet clean glass surface, and also the glass surface after the plasma treatment. The scale of this graph is the same, and you can see here that if we discuss only the carbon concentration, in the first image in the top left corner, there is a huge or high concentration of carbon. The graph is uniform because of basically it's the same image. This one is the same as that one, only the scale is different. And we see that after the plasma treatment, the concentration of carbon decreased to less than 5%, and the surface is very uniform. And we see this good uniformity also on the map of oxygen too. We didn't study only the micro-uniformity, but also the macro-uniformity. And for this experiment, we treated really large samples of glass sheets using the array of 5 DCSBD units. And we analyzed the variation of, again, the variation of carbon, oxygen, and silicon. And we can see that the variation of, for example, this ratio oxygen to carbon decrease from more than 30% to less than around 12, 13. So the application. We plasma treated glass, and we created the laminated glass. We did the experiment also in the real production line for the laminated glass. This is one section. The machine direction is from the left to the right. The glass is coming from the washing machine, and then on the right-hand side, there is the real lamination process. You can see how the glass is treated by plasma when it's passed through the plasma region. We took this glass and then we analyzed it. We use different type of analysis. We carry out a drop ball test, 4-point bending test, pendulum test, also some stability tests. All stability tests we carry out prove that there is no change if we run like a temperature stability test, humidity test, or UV radiation test. So let's discuss, for example, 4-point bending test and pendulum test. We created laminated glass using the standard wet cleaned glass, and we measured the breaking force of this sample around 650 newtons. And for example, plasma treated or laminated glass created using the plasma treated glass, and we measured the breaking force 950%, which is improvement around roughly 50%. So there is also a possibility to treat not only the glass, but also, for example, the interlayer. Because of using our technology, it's possible to treat polymer materials. And about this work, there was a talk of my colleague Dusan Kovacic, but unfortunately, he just finished his talk in another section. Another utilization of DCSBD plasma is that we can treat also flexible glass, not only flat float glass. Maybe this might be interesting for some of you, that we can treat also this kind of glass. So this is my summary. I presented to you our atmospheric plasma DCSBD technology for surface modification of glass. I show you that this plasma treatment has some effect on the surface of glass. We created laminated glass using plasma-treated glass surface. We did some tests, which I hope prove that the plasma treatment has some positive effect on the final product. And we think that this technology has benefits which can be maybe utilized in the real production of laminated glass. Thank you. That's all.